Today we're going to learn how to fit a plane to a data set. Okay. And so what we have here is we have points x, y, z. We have an extra coordinate here now. And we have this plane, which is going to be defined by three different constants. Okay. A1 will be the just constant. A2 will be the constant attached to x, the x's, and A3 will be the constant attached to y. Okay. And it's what we're going to do is, just like in the other two cases we've looked at, we are going to minimize the square error. Okay. So what is really in the parentheses here is zi minus zi hat. So this is from the data, and this is going to be from the plane. Okay. And so subtracting these gives us the error, or how far off the plane is from the actual data point. Okay. So I'm going to add a little bit more to this sentence here. Is minimized. And so to minimize this, we're going to take a partial with respect to A1, A2, A3, and we're going to set those partials equal to 0. Okay. Let's go ahead and do that. Okay. Well, let's start off with the partial of Q with respect to A1. And I'm going to stop writing I equals 1 to n on all these summations just because it's going to get a little tedious. But all the sums are going to have I equals 1 to n on them. Okay? So it's just implied. Okay? So let's take that derivative with respect to A1. Bring down the 2. Z sub I minus A sub 1 minus A sub 2 x sub I minus A3 y sub I, all to the 1, which we don't need to write that 1 there, and then times the derivative of the inside. So if we were to differentiate with respect to A1, then is what we would expect to get out here from the chain rule is A times minus 1. Okay. Let's take the next partial. The partial of Q with respect to A2. And like I said, I'm not going to write I equals 1 to n, but you'd get a 2 coming down. So the beginning of this is going to look exactly the same. But once we go to take the derivative of the inside with respect to A2, that's going to leave us with a minus x sub I. Okay. And one more partial. Okay. We're going to take our partial of Q with respect to A3. Okay. And so this is 2 times all that same stuff. But when we go to apply the chain rule here, we're going to need times a minus y sub I. So now that we've taken the partials, we want to set these partials equal to 0. Okay. Let's go ahead and do that. Okay. So 0 equals, and note all of these have this 2 here. So if we were to set these equal to 0 and divide by 2, we could wipe out those 2's. So we're just not going to write those. And we're going to split up our sums. And we're going to distribute these terms here. Okay. Let's go ahead and do that. Okay. So we'll have our first sum here, which is going to be of minus z sub I. Okay. And then when I get to the next term, we're going to have plus, right, because we're distributing a negative. plus the sum of A1, and then plus, and I'm going to write the A1 even out front. I'm going to say A1 times the sum of just 1. Okay? Right? This A1 is a constant. Okay? So I can pull it out of the sum here. And then plus A2 times the sum, okay, of x sub I. Okay? Again, distributing that negative makes this positive. And then one more, plus A3 times the sum of y sub I. Okay? And let's do that with these next two. Minus the sum. And it looks like we're going to have a z sub I times x sub I. And then plus A1 times the sum. Okay? And this time, again, we're distributing minus x sub I. So this is going to make this a positive x sub I here. Okay? And then plus A2 times the sum. And if, again, we're distributing this x sub I, that's going to give us an x sub I squared plus A3 times the sum. Okay? And so this time we're thinking about the x sub I times y sub I. And then we'll move on to the last equation. Okay. And for the last equation, it looks like it starts off with a y sub I, z sub I. And this next one is the sum of the y sub i's. And the next one would be the sum of the x sub I times y sub i's. And then the very last one here is going to be y sub I squared. Okay. All right, so we have our system of equations now. Let's write this in a slightly different format so that you can see that is what we actually have here is something that can easily be solved using a matrix. Okay, so I'm going to actually pause the video for a second to do my next step here. All right, so I've added in this extra step that you can see here now, this extra line, and all we've done is we took all these first terms in each equation and added them to the other side. You can see they're now over here on the right. Okay? And so there's no negative, any negatives in front of any sign or any sums here anymore. But is what I'd really like you to be able to see is that all these highlighted pieces, which I have a few more here still to highlight. But these are the sums of really our data points. So all these sums that we're looking at, these are all just filled with constants. Okay? And in fact, if you were to add and multiply a bunch of constants, you get a constant. So every one of those highlighted pieces is a constant. So you have A1 times a constant plus A2 times a constant plus A3 times a constant is equal to a constant. This is just a linear equation. Okay? This is a system of linear equations. Let's go ahead and write it in matrix form really quickly, and then from there is what we'll do is we will try this out in MATLAB. Okay? Here is our matrix equation, and let's specify, we'll call this A, we'll call this B, and we'll call this little a. Okay? So we're going to have to generate this matrix A using a for loop. That way we can calculate those sums. And same goes for the vector B, and we want to solve for the vector A. So and is what we'll end up putting in MATLAB after we generate those matrices, is we'll want to do A backslash B, or sorry, big A backslash B in order to find those coefficients. Okay. So let's go into MATLAB and do that. So we have a data set in Canvas under modules, and it's called wave height. And so I'm going to go ahead and import that right now. Okay. All right, and you can see all the data is highlighted. Let's go ahead and hit import. And you can see up there, it gave me a message that's fading away that says the following variables were imported, so we know we're done with that. So we'll hit the X here to go back to the main screen. And here we are. And let's go ahead and convert our data from a table to an array. That way we can do things with it. Okay, when it's in that table format, there's nothing we can do with it. And so this was called wave height. Okay, wave height. Let's go ahead and run it. Make sure we don't have any errors here. I need to hit editor and run. Okay. So no error messages. Okay. And let's split our data up into X, Y, and Z. Okay. Because each column right now corresponds to a different thing. The first column was we might have to look back in this one. Here we go. The first column was the duration of the wind. Let me see if I can make this a little bit bigger. Yeah, the duration of the wind in hours. The next thing was the wind speed in knots, and the last thing was the wind height in feet. So what we're trying to do is trying to predict the wave height based on how long the wind's been blowing and at what speed it's been blowing. Okay, that's what this data set here is all about. So let's get out of this, and we'll say X equals, okay, and we're going to want this to be the first bit of data here, which is colon, comma, 1. So that's the first column. Y can be the second column, or is the second column, and Z is going to be the third column, and we're going to plot this. Okay. We'll do, and to plot in 3D, you actually have to use this plot 3. So X, Y, Z. Let's use the asterisk. So I'm going to want to put a little asterisk there. Okay. So that should do it. But let's also label these things. So how about X label? Okay. So this was hours or duration of the wind. The Y label. This was the speed of the wind in knots. Okay. And Z was the wave height in feet. Okay. Let's go ahead and try and run this. There we go. And I'm going to move this around so you can see this actually has some curvature to it. Okay, if I move this around a little bit. Okay, right? This thing's not perfectly a plane by any means. Even though that this is not best fit by a plane, we are going to fit a plane to it anyway because this is the 3D data set we have. Okay. But one of the things you'll have in your homework is you'll actually take a model or a data set, you'll linearize it, and then you'll use this multiple linear regression that we're going to do, and then you'll convert it back to the form it was originally supposed to have, and you'll be able to fit curved things curved surfaces to data sets. But we're just going to do a plane here. Okay. All right, so next, now that we have our plot done here, so we know what it looks like, we can start setting up A and B. So you might remember A was a 3 by 3 matrix, and I'm just starting off with zeros in it. And I'm going to do the same thing with B, which was a 3 by 1. Oop. And this is just because we're going to create a for loop, remember, that adds together all our terms. And so before we start adding things in, we're going to have these things be filled with zeros. Okay? So for I equals 1 to whatever the size of our data set is. And so you can actually see on the side here, there are going to be 49 elements in X, 49 in Y, 49 in Z. But if, you know, things were getting a little messy here, or you wanted this to be a little more general, you could say, hey, let n equal the length of really any of those X, Y, or Z. Okay, they should all be the same length. Okay, and if there's not, there's a problem. Okay, if they're not the same length, there's a problem. Okay, okay, so there's that. Next, we want to start setting up that matrix A. Okay, so let's take a peek at it. Okay. You can see in the first, in the far left entry, we're going to be adding ones over and over. Okay. So I'm going to put a 1 here. And then I think the next spot was X of I and then Y sub I. So add X of I's and then add Y sub I's. Okay. X of I, Y of I. Okay, and then if we move down to the next row, what are we adding? X of I squared, X of I, Y sub I. Okay. So X of I squared, and X of I times Y of I. Okay. And then if we move on to the last row, I believe it starts off with Y of I, X of I, Y of I, and then Y of I squared. Okay, so let's do that. Y of I, and then X of I times Y of I, and then lastly, Y of I squared. Okay, and let's just space things out here a little bit so that this is a little easier to look at, a little easier to read. Okay. So the only other thing we have left to do here is add A. Okay, so is what will happen here. Let's just take a look at maybe this entry right here. Okay. Is what this is going to do, this for loop, is it's going to take X of 1 and add 0 to it, right? Because the first entry there, or all the entries are 0 at the moment. Okay. And then when I equals 2, it'll take your X of 1 that you had there and add X of 2 to it. Okay. And then the next one would add X of 3 to what we have. And then the next one would add X of 4 to what we have, and so on until we're done. Okay. And we want B to function the same way. So let's go ahead and write B. B was meant to be Z of I, X of I, Z of I, Y of I times Z of I. Okay, let's go and fill that in. Okay, so Z of I times X of I, and lastly Z of I times Y of I. Okay, and we just need to add B to this. So there's our generation of the matrices A and the vector B. Let's go ahead and compute our coefficients here now. A equals A backslash B. Okay. And is what we want to do is with these coefficients, we want to write this equation that we have here in OneNote. Let me go up here and find it here. This thing. We want to take the first coefficient plus the second times the x's plus the third coefficient times the y's. Okay. Let's go in and do that. Okay. So there's more that I'm going to have to fill in between here. That's why I've left a little bit of space. But so z equals, how about, a of 0, so there's our first coefficient, plus a of, let me fix that, a of 1, our first coefficient, plus a of 2, our second coefficient, times x, plus a of 3, so that's our third coefficient, times y. Okay. And you may be noticing that I'm using capital X, capital Y here, and that's because in the line above this, I am going to use the mesh grid function. Okay. But in order to use mesh grid, I need a list of x's and y's that I want to actually plug in to the equation for z. Okay. So I'm going to need to use linspace to create that x and y vector that I want. So maybe I'm going to say x0, y0 to describe those. But we still need to make them. So y0 equals linspace, and x0 equals linspace. Okay. And let's go 0 to 70 in the x's, because I believe the largest, let's just look. Let's go in here into the table. So our x's here, you can see they go from 5 to 50. So in our linspace here, let's actually go 0 to 60. And this is just a plane, so it's not going to require a lot of points in order to plot this. Let's just say 10. Okay. And let's go 0 to something else here for y0. Let's see what the y's were describing. Okay. They were describing wind speed, which it looks like varies from 10 to 60. So we'll go up to 70 then for that to give a little bit of wiggle room. And again, just 10 would be enough. Okay. All right. I think we have everything we need here in order to fit this plane to our data. Okay. I want to point out before we hit run, this should not fit our data perfectly. Our data clearly would have been fit better by a curved surface rather than this flat plane. Okay. But once we move the shape around a little bit, you'll see it actually fits the data actually pretty well. Okay. Let's go ahead and hit run. Okay. And you might be wondering, well, where's the plane? Well, we never typed in, hold on. Okay. So where's our plot? Our plot of the data was here. So we hit hold on there. Now we should get both. What did we use down here? We never used, and I'm going to suppress a couple more things here. I think got a little bit ahead of myself here. I want to do plot, or how about, since it's a 3D thing, surf of x, y, z. Okay, and let's do, let's just do that. Surf x, y, z. Okay. There we go. Okay, so from this angle, you can't really tell whether it fits the data well or not, but let's move it around a little bit. Okay. Right, the distance between that plane and those points doesn't look actually all that far off. But again, I could imagine us creating a curved surface that would fit this better. Okay, and we'll see a couple ways to do that here in the next, actually tomorrow. All right, but that is it for today.